Is the seventh lecture of module 5. This is the continuation of the previous lecture, that is principle of vector control or field oriented control. In the case of a three-phase induction motor, it has a three-phase stator winding. So this three-phase stator winding creates the current and the MMF, which are sinusoidally distributed along the air gap. And as we know, the stator currents IAS, IBS and ICS. There are three stator currents because it is a three-phase stator winding. They are 120 degree apart. Three-phase stator currents are having 120 degree phase difference from each other. And this IS is the current space vector. This space vector represents the instantaneous magnitude and angle of the sinusoidal distribution of the current vector in space. So IS represents the stator current, and IS is a space vector also. Its magnitude as well as angle varies with time. It keeps on rotating. So since we are going to control the induction motor with vector control, we have to incorporate the features of a DC motor. That means the vector controlled induction motor drive can be controlled as a separately excited DC motor drive. So to ensure the similarity, we have to get two components for the stator current, two different components for the stator current. They are torque producing component and flux producing component. For that purpose, we have to transform the three stator currents into two mutually perpendicular stator currents, one being the flux producing component and the other being the torque producing component of the stator current. So in vector control, the variables from the physical three-phase ABC system are transformed to a stationary coordinate alpha beta system. That means a stationary coordinate system with two components, one along alpha and other along beta, two axes. These are the two axes. Alpha and beta are the two perpendicular axes in that system. And then again we will transform this system of currents into a rotating reference frame system, that is DQ reference frame, which is equivalent to the armature and field currents of the DC motor. Now let's see how these transformations are done. The first phase of transformation is known as Clarke transformation. In Clarke transformation, the system of ABC, the system of currents ABC are transformed to a system of currents alpha beta. That means the system of currents along A, B and C, which are 120 degree spatially displaced, are transformed to a system of two currents IS alpha and IS beta. That means IS alpha is along an axis alpha and IS beta is along a perpendicular axis beta. That's why it is mentioned as ABC to alpha beta system. So using Clarke transformation, three-phase components are transformed into a two-dimensional coordinate system. Now for this purpose, we use a transformation matrix known as Clarke transformation matrix. This is how the transformation is done. So IS alpha and IS beta are obtained from the transformation of ISA, ISB and ISC, the system of three currents, three-phase currents. And this is the transformation matrix for Clarke transformation. Now, for the control system, we need an inverse transformation also. For that purpose, we have an inverse transformation matrix. This is the inverse transformation matrix. So, in inverse Clarke transformation, the alpha beta system is converted back to ABC system using this transformation matrix. This we will discuss later. Next is the second phase of transformation in vector control, that is path transformation. Here the transformation is from alpha beta to DQ frame. So this alpha beta system was obtained from Clarke transformation, and after that we are using that system of currents IS alpha and IS beta are used to transform to a DQ system of currents. Now let's see what is the DQ axis. Here this is the D axis and this is Q axis, and D and Q are mutually perpendicular, and one more thing to be noted is that the angle between D and alpha is equal to theta. Another thing is the D axis lies along the rotor flux vector. Rotor flux vector and D are aligned. This is how the transformation is done. So we can directly write the equations for ISQ and ISD. ISQ and ISD. The components of the stator current vector IS along Q and D can be easily written from the figure itself. So these are the equations. ISQ is equal to the component of IS alpha along ISQ. That is IS alpha sin theta. IS alpha sin theta will be in this direction. So minus of IS alpha sin theta will be in this direction. So minus of IS alpha sin theta plus IS beta. This angle is equal to theta. So IS beta cos theta. IS beta cos theta. So we have obtained the expression for ISQ. Next ISD. That's also very simple. ISD, this component ISD is equal to IS alpha cos theta plus IS beta sin theta. That's also very clear. Now, as in the previous case, here also in the control system we will have to perform the inverse transformation also. For that we have an inverse transformation matrix too, and this equation can be expressed as a matrix like this. This is the path transformation matrix. This equation represented in the matrix form. Similarly, the inverse path transformation matrix can be written like this. The stator voltages represented in the DQ rotating reference frame are transformed to a two-phase orthogonal alpha beta system. So we have to keep in mind that DQ frame is a rotating reference frame because DQ frame rotates along with the rotor flux vector. D axis is aligned with the rotor flux vector. So DQ frame rotates along the rotor flux vector in this case. And this is the inverse transformation matrix. The inverse, what is the necessity of inverse Clarke and path transformation, that we will discuss in the next session. Now, after the transformations, we obtained two vectors, that is IDS and IQS, and from the equivalent circuit of the induction motor, it's very much clear that the components of the stator current IS, that is IDS and IQS, are the flux producing component. IDS is the flux producing component which is aligned along the rotor flux, and IQS is the torque producing component. And this is the representation of IS. IS is equal to root of IDS square plus IQS square. Next we will discuss the block diagram of vector controlled induction motor drive. This is the motor to be controlled, and it is fed from a three-phase inverter, which is again fed from the DC power supply. And this inverter is controlled from this control signal or gating signals. Let's see how these gating signals are produced so that this induction motor is controlled via vector control. Here, the speed of this motor is sensed using a sensor, and that speed or motor velocity omega is fed back to this point. Here, the target velocity or reference speed is compared with the actual speed, and the speed error is given to the velocity controller or speed controller. It will be normally a PI controller, and that the output of that velocity controller will be the reference value of ISQ, that is the component, the quadrature component of stator current. That is the reference value of ISQ. Now let's see how the actual value of ISQ and ISD are generated. Here, the stator currents of the induction motor, that is ISA, ISB and ISC, are measured from the stator of the induction motor, or just we can see the output of the three-phase inverter is measured, and those three currents are given as the input of the Clarke transformation block. The Clarke transformation block will transform the ABC system of ABC currents into a system of two currents, IS alpha and IS beta, as discussed earlier. And this system is again given to a Clarke transformation block, which transforms the alpha beta currents to DQ currents, that is ISD and ISQ, where ISD is the flux producing component and ISQ is the torque producing component of the stator current. Now the actual value of ISQ is fed back, and it is compared with the reference value of ISQ, and the error is given to the torque controller block. Now let's see what happens here. Here the target velocity is given to the field weakening block, and it is given to the output of the field weakening block is the reference value of ISD, and the reference value of ISD is compared with the actual value of ISD, and the error is given to the flux controller block, and the output of the flux controller block is VSD ref, that is the reference value of the stator, the quadrature component of the stator voltage, that is the applied voltage to the stator. The reference value of the applied voltage to the stator are obtained here. The output of the flux controller is VSD ref, and output of the torque controller is VSQ ref. So D and Q component of the stator input voltage are obtained, and that DQ, the voltages in the DQ frame are given to the inverse Clarke transformation. Clarke raised to -1 is represented by inverse Clarke transformation block. Here DQ components are transformed into alpha beta component. So for this purpose the inverse transformation matrix will be used, and the output is Vs alpha ref and Vs beta ref. These are the reference values of the alpha beta components of stator voltage, and from here these voltages, these reference values are given to the inverse Clarke transformation block or PWM modulator, or both. This block, the structure of this block is based on the type how we implement this structure system. So here let's consider the case when this block consists of an inverse Clarke transformation block and a PWM modulator. That means here the reference values of Vs alpha and Vs beta are transformed to the ABC components of stator current, that is VSA, VSB and VSC reference values. All these are reference values. Then using those reference values, based on those reference values, the PWM modulator will produce the gating pulses for the three-phase inverter, so that the three-phase inverter will produce the output voltage, that is the stator input voltage of induction motor, according to the reference values obtained from inverse Clarke transformation block. That's how the three-phase induction motor is controlled via vector control. Thank you.